Good morning. How is everybody doing? All right, so it's really a pleasure to be here. Uh, I was going to talk about boron and metal boride nanoclusters, but after hearing all the talks yesterday and about the content of the EOC, so I actually added some our gold cluster work. Actually, I worked late last night. I thought I want to fit it to this meeting. Uh, all right, so let's start from the beginning, right? So what are nanoclusters, right? So my definition is these are aggregate of atoms, and their properties and structures change as a function of size. Clusters are really the foundation of nanoscience. So this is the bottom-up approach of nanoscience, right? We heard about yesterday about the third dimension of the periodic table. So this is how we build the third dimension of the periodic table. So in the early days of cluster science, so mass spectrometry was a very important tool because we need to know what clusters we have made. So I will highlight a couple of examples. There were two major discoveries simply by doing mass spectrometry research. So one of these is on sodium clusters. So we heard about yesterday from Professor Lai-Sheng. So Professor Schumacher actually was the very first scientist to produce sodium clusters in the most smaller size range. So this is a work done at Berkeley in 1984. They simply took an oven and heat up sodium and let the sodium vapor to aggregate. They look at the cluster coming out of the source. They ionize the electron impact. So that's the intensity of the cluster. This is the size. You see here the intensities are not continuous, right? So you see some clusters have a higher intensity than others, right? Particularly this is 8, 20, 40, and 58. And they explained this with the so-called electron shell model. So the electron shell model actually was a nuclear physics model. And you see here that the electron shell model predicted that you have shell closings at these different angular momentum states, and that explains the stability. So this electron shell model is really powerful. It can explain a lot of properties of free electron metals. So this really forms the foundation of super atoms. So another really important discovery in cluster science, just simply by doing mass spectrometry, was the discovery of Buckminster fullerene. So this is a carbon cluster distribution coming from, this is a laser vaporization source. What you see again here is the intensity as a function of cluster size. You see here, this is about carbon 40 to carbon 86. So what do you notice here, right? So in the bottom, so you see there's a couple of clusters, their intensity are a little bit different from the others. So if they change the source conditions, so what they did is they simply add a kind of a more cooling channel, right? So as they add this cooling channel, they find that this carbon 60 intensity become higher and higher, and they actually have to come up with explanations. That means these two clusters must be very, very stable. And particularly for C60, they came up with a solution. It has a soccer ball structure, right? So if you play soccer, the soccer ball has 12 pentagons and 20 hexagons, right? With 6 vertices. If you put a carbon atom at each vertices, that's carbon 60, and that's the name, right? So this was in 1985, and 5 years later, a group of astrophysicists, they were interested in carbon dust. So they simply were taking a carbon rod and they start an arc and they evaporate the carbon, they collect the dust, they find in that dust, if you dissolve it in benzene, and you get a beautiful magenta color, and you filter that out, and you get these beautiful crystals, and that's fullerite, that's Buckminster fullerene in the solid form. So this is the third form of carbon. We've Before that, we know carbon has two forms, right? It's diamond and graphite. So now this is another form. Now, if you actually look at the materials at the electrode, the solid materials at the electrode and the microscope, actually you find the carbon nanotubes. So carbon nanotubes, the discovery of carbon nanotubes was a direct consequence of the bulk synthesis of fullerene. Of course, subsequently, graphene was also discovered. And so these two discoveries, of course, won Nobel Prizes. The fullerene won Nobel Prize in chemistry in 1996, and the discovery of graphene won Nobel Prizes in physics in 2020. So what are we doing, right? So what we are doing in my laboratory is to study clusters as a function of size using photoelectron spectroscopy. So we actually do two things in our lab. We study clusters. So this is essentially to build the third dimension of the periodic table, like we heard yesterday. We have another effort in our lab is to study molecules, negative ions coming from solution samples. And particularly recently about dipole bound states. So this was the topic that I spoke about in the department yesterday, but I'm going to focus on clusters today, the third dimension of periodic tables. Now, over the years, my lab has studied clusters almost across the periodic table, almost all the transition metals and some main group elements, including oxide and carbide. So what I was planning to do was to focus on boron clusters for this lecture. As I mentioned, after I heard all the exciting science about atom-precise clusters, I decided to also mention some effort about our synthesis of gold-20 cluster, so specifically. So my lab is a physical chemistry lab or chemical physics lab. We do spectroscopy and we make clusters one atom at a time, and we study their properties. But we also like to, sometimes we want to see whether we actually can make these materials and hold in our hand, like a buckyball, right? The buckyball was discovered in the gas phase, one molecule at a time, and then it was synthesized, then that became the foundation for a new branch of material science. So let's start with gold. Okay, so gold we know is the most inert metal in the whole periodic table. But if you make a gold to become very, very small size, it actually becomes catalytically active. So in the late 1990s and the early 2000s, the study of gold nanoparticles and gold clusters were a very active field, because we wanted to understand why gold nanoclusters or nanoparticles are chemically active. So what we try to do among any other cluster group is to understand at the fundamental level, what are the structures of these small gold clusters, what are their properties, how they change as a function of size. So we already learned from Professor Lai-Sheng yesterday that small gold clusters, they are planar, right? This was actually initially observed experimentally from ion mobility experiment by Professor Koppes' lab. So we were using photoelectron spectroscopy to study these clusters, and we find that if you go, so the transition from 2D to 3D happens on 12 or 13 atoms. So we find that, okay, 14 and 15, they definitely are 3D. And in fact, the 16 is a beautiful cage structure. So that is our first golden buckyball. And now when we get to gold 20, we find it has this beautiful tetrahedral structure. This is very stable, and the photoelectron spectrum, I will show it later, it has a huge energy gap. It's even bigger than carbon-60. So this cluster later was imaged using TEM. I'm sure if you put this cluster and your cryo-TEM, you will see an image like that. It has the tetrahedral, a triangular structure. And more exciting, right? So this group, this is Wolfgang Habisch group, they deposited the gold 20 in a neon matrix, and they looked at the fluorescence. They find that this cluster in neon matrix has near 100% fluorescence, and it fluoresces at around 1.680 eV. So this is the photoelectron spectrum that we measured about the gold 20. You look at this energy gap, right? So that means gold 20, it's a semiconductor, right? So bulk gold is the best conductor, but at 20 atoms, it's a semiconductor. It has a very large energy gap. The energy gap is about 1.7 eV, and that's almost exactly what's measured in the fluorescence spectroscopy, right? Fluorescence spectroscopy, you excite the electron to the S1, the lowest excited state, then it comes back, and that's exactly should correspond to this energy gap. You look at, this is the photoelectron spectrum of carbon-60. You look at the energy gap of gold 20 is even higher than C60. That means gold 20 is extremely stable system electronically. So we asked the question, right? So can the gold 20 pyramid be synthesized in bulk quantity? Now, this actually, initially, this was prompted by an email from Professor Haruta. So if some of you may know Professor Haruta, he was the pioneer of gold catalyst, right? His group, among others, discovered that gold nanoparticles can become gold catalyst. When he saw our paper on gold 20, he wrote me an email. He said, can I have some samples? He wants to test the catalyst. So that just dawned on me, okay, we actually need samples. Can we make samples? So we asked the question, right? So now we certainly cannot collect these classes one atom, one molecule at a time, like what Professor Lai-Sheng was doing. So we needed to make at least milligrams of quantity. To do that, we need to come to solution chemistry and trying to synthesize this and protect it with the ligand. So we have a very simple idea. So to protect gold 20, right? So what do we want? We want to use phosphine ligand. We want to cover basically to coordinate the four corner atom, and then we still maintain the tetrahedral structure. Now, you heard about almost all the gold nanoparticles synthesized were using SIO ligand. Now, SIO is a very strong ligand and it forms covalent bond with the gold. So SIO would for sure destroy this structure. Now, phosphine is a weaker ligand and it has a chance to maintain this structure. So this is a kind of computational model. This kind of Van Waals radius. If you consider triphenylphosphine. So this is our very simple idea. We want to use this as a ligand, and when we reduce a gold reagent to see whether we actually can make this cluster. So this is our first synthetic effort in my lab, right? This is right after we publish our gold 20 paper. So then we actually look at the solution. We use the electrospray, look at what's coming out in that solution. When we reduce the gold agent with boron, sodium boron tetrahydride, and we actually did observe a gold 20 cluster with 4 phosphine. This is with actually 7 phosphine ligand. This is with 8 phosphine ligand. So this is a dianion. So we were able to isolate this gold 20 with 8 phosphine ligand, and we were able to do CID, and we find 4 of these ligands can be easily knocked off. So we saw that this provides the evidence that this gold 20 pyramid could be synthesized in solution. So now we have 8 ligands, probably we have 4 ligands coordinate to the corner, and the other 4 ligands coordinate to the 4 face. Now the 4 faces, the ligand binding probably is weaker. That's why we can easily knock it off. But you look at this mass spectrum, right? So the gold 20 pyramid is a very minority species. So how can we actually synthesize this gold 20 more selectively and in larger quantity or in higher yield? So our idea was, okay, perhaps we need to use a diphosphine ligand. So basically our assumption was, okay, so if we have the right ligand, we might be able to capture this cluster, right? So the question is, what is the right ligand? So we thought maybe the diphosphate ligand might be promising. So we bought all the diphosphate ligand we could buy. So that is from one CH2 group up to 6 at that time. We could buy them. And we tested all of them. We couldn't really make go 20. So now this was the time I was at Washington State University. I was a physics professor. And when I moved to Boron, my plan was to hire some hot undergraduate students to synthesize this ligand. And so what we want to do is we want to make this ligand so we could only buy up to 6 carbons. So we want to make, say, this long chain from 7 carbon to whatever length we can make. Actually, we ended up making, so in collaboration with our organic colleagues, we made this diphosphate ligand from 7 CH2 group up to 12, and we're testing what we could make. Now, one of these ligand worked, and that is this ligand with 8 spacer, 8 CH2 group, and we were able to capture a gold cluster, but this time with 22 atoms. So this is a mass spec of this cluster after we did some separation. We were able to grow a crystal, and we were able to solve the crystal structure. This is a beautiful structure. This is a gold 22. Actually, it contains, it's basically a dimer of gold 11, right? You have 2 gold 11 units. They dimerize, they share a square face. What's beautiful is this, there are 6 ligands, right? So you have a 4 bridging ligand, then you have 1 ligand on each unit. So what's important is these 8 gold atoms in the interface between the dimer, they are not coordinated, right? So they are free. So this is the essence of a design. We want to make gold clusters, or the gold 20. So with in situ active sites, right? You have atoms on the surface which are not coordinated. So those should be the sites that catalysis can happen, right? So we have very well-defined catalytic sites. And this is the first cluster that was ever made that you have a bulk quantity and you have actually uncoordinated gold sites. So we later collaborated with Professor Zili Wu and Dian Jiang to look at the CO oxidation of this cluster, and we found this is extremely active, right? So this is much more active than the gold 25 silane coordinated cluster. Even at room temperature, it has activity. If we do a heat treatment, this is on TiO2 surface, even up to about 400 degree K, the activity is very, very good. No, but this is not what we want, right? So we still want our gold pyramid, because this cluster not only it will have good catalytic properties, you should have also very, very important photo physical properties. So we came upon this ligand. This is a tetraphosphate ligand. We saw that, okay, this ligand actually we simply just found in the catalog. We were looking for what kind of phosphate ligand can we buy. And so my students found this. I said, okay, this is nice. So perhaps we can have 4 ligands, then they capture each phase, and this will be perfect. And we got this ligand, and we actually find a very high yield synthesis, and we made a 4 ligand coordinated gold 20. We actually made gold 20. When I saw the mass spec, I was very excited. I said, okay, we have made this baby. But when we solve the crystal structure, so nature can always play a joke on you. It actually, I thought, okay, you have 20 atoms, you have 4 ligands. So it has to be the tetrahedral structure. And in fact, the structure is very, very different from what I thought. It actually, the gold core essentially has a gold 13 icosahedra. That's the core, and with a second layer of 7 atoms. Okay, you have 13 is the gold, so these are the 7 gold atoms. Actually, it's like a propeller. So this gold core actually is chiral. And you actually look at the coordination, and so every atom is coordinated on the surface, and except one atom in the middle. And this is extremely stable cluster. And we try to do ligand exchange. We can't do, this stable, this is, it's a high yield. We can make 50% yield. And we try to do ion exchange. We couldn't do anything. So we saw the chemical that this is dead because you don't have active site on the surface, right? We cannot open up active sites. All right, so we got very close to make our goal 20, but not quite yet. So now we want to step back. We have this goal 22 with uncoordinated site, right? So it should have really interesting chemistry. So we were actually stimulated by this paper by Dian and Jiang. So this is after he saw our goal 22 paper, he actually published a paper suggesting that stronger than platinum hydrogen adsorption in goal 22. So what his calculation suggests is that, okay, this gold 22 cluster, the 8 uncoordinated gold site should be able to dissociate the hydrogen to form a hydride. Now, this is exciting. So then we saw that, okay, so if we take this gold 20, we bubble hydrogen through the solution, we should see gold hydride. I saw that would be a demonstration that this could be a very good hydrogenation catalyst. So I was able to recruit a student in 2019. This is Jia Dong, and he was actually not a synthetic person. He came to Boron, wanted to do nano chemistries. He wanted to join the nano group in my colleagues group, and he was not able to join because his background was physical chemistry. He came to me, he said he wanted to do spectroscopy. I said, well, why? Since you want to do nano, I have a really interesting nano project. Why don't you try this? So I said, why don't you simply bubble hydrogen through this gold 22 cluster? If we can see hydride, then you have your first paper. Now, he bubbled the hydrogen for 6 months, and he didn't see any hydride. I told him, I said, okay, work this for 8 months, because at that time, my previous student was still around. I said, if you still can't make any progress, you can come back to do spectroscopy. So we have to make a decision, right? He couldn't see anything, so this is dead end. Except that one day he came to me. He said, well, I saw hydride actually without bubbling hydrogen. And so this is the mass spec. I have to, so this is basically a fresh sample, right? Freshly synthesized sample. So I must say that we actually saw this back in 2014. But back in 2014 at Boron, we did not have a high resolution mass spec. So I sent that sample to my colleagues at PNL, Pacific Northwest National Lab, and they measured the sample 1 month later, and they saw one hydrogen. We saw that hydrogen is coming from electron spray. We didn't pay attention. But by this time, so we actually have a high resolution mass spec, and he synthesized it, he took it to the lab and measured immediately. This is what he see. And of course, now to prove that, we said, okay, let's deuterate it, right? So if we start with BD force reducing agent, and indeed, and we were able to make the deuterated version. So now we actually know this is a hydride. So that's a problem, right? So the question is, in 2014, did we actually publish something wrong, right? Because the X-ray is not sensitive to hydrogen. Do we actually have the hydride? So for a few days, I was actually quite nervous, right? Did we publish something wrong? It turned out that this hydride, right? So this is the gold 22. The freshly synthesized sample is the hydride. It turned out this is metastable. Even when we try to take the proton AMR, right? Even at room temperature, as we are taking the AMR, we see free H2 signal. And if you heat this to even 50 degrees, you see the H2 is very high signal. So what happens is to grow this crystal, it takes a week. So during the crystal growth, in fact, the hydrogen all disappear. So Jiao actually spent the next year to figure out what is the hydrogen loss mechanism. Actually, he did a fabulous job and figure out exactly how this hydrogen is lost. Actually, this is all done in this really extensive paper. Now, but this hydride, right, it's metastable, and this particular cluster is also not very stable. The shell life is not very long. So we go back to, so when we actually made this cluster, right, so you see this linker, this is just a CH2 group. We saw that if we want to access these gold atoms, right, so to do hydrogenation, right, so we need a proton. Then we saw that if we can change this to a polar group, this may help the catalysis to access this side. So this is my previous student, Chen Fan. Then so we tried this linker, right? So this is an ether group. This is about the same size as this. And so when Chen Fan tried to use this ligand to synthesize this same cluster, he got a gold-22 cluster. But now it consists of 7 ligands instead of 6 in this case. So at this time, but he could not grow a crystal for this cluster. So we did the chemical physics measurement, and we were able to conclude in this cluster at least that there's one gold 11. We don't really know anymore. So this paper was published in Small in 2016. So to make a long story short, basically, okay, Chen Fan, he found a new cluster, but he missed the discovery of a gold hydride in the second time. Because after Jiao discovered the hydride in this cluster, he went back to this cluster again. And so this is what Jiao found. So in the freshly synthesized sample, actually, it is a trihydride. But actually, Chen Fan, back in 2016, in the mass spectrum, we saw very clear the trihydride. We just ignored it. We saw the other hydrogen coming from the electrospray process. So, of course, now we can easily prove it. If we just use the BD4 as a reducing agent, we can see the deuterated form. Now, the beauty of this cluster is it's stable. This is basically in a solid form, it's stable forever, right? So he put it on the shelf for 2 months, and we took the mass spec again. There's no change. Now in solution, there will be degradation in a few weeks, but in solid form, it's very stable. But this cluster is a very hard to grow crystal, so we could not determine the crystal structure. So Jiao actually, he was a good synthetic person, but he was also very good with calculation. He actually did all the calculation himself. So we saw that, okay, now there are 7 ligands, right? So we actually now know that this should also be a gold 11 dimer, right? But now they share a triangular phase. So that's where the trihydride, the hydride is bridging the uncoordinated sides. Since we have 7 ligands, so that means that there could be only an odd number of bridging ligands. We can have 1 bridging ligand or 3 bridging ligands. So he did the calculation. He found that 1 bridging ligand is actually the most stable one. The bridging structure is higher in energy. So just earlier this year, we collaborated with Professor Kapis' group. We did ion mobility on this cluster. We actually find there are 2 isomers. The main isomer actually is the isomer with the single ligand. There's a minor isomer actually is with the 3 ligand. So in the meantime, so we actually, because this trihydride is so stable, we actually tried to, I collaborated with my colleague, Professor Xiaoheng Sang, to do a CO2 reduction. So we found that this gold-22 trihydride cluster is a very active CO2 reduction catalyst. It can reach Faraday efficiency more than 90% at pretty low overpotential. All right, so JR is really an amazing student. So when he was doing this synthesis, he discovered nanocluster using diphosphine ligand. He discovered a new gold-11 cluster. Now, gold-11, of course, was known for a long time. The gold-11 phosphine cluster was synthesized in the 1970s, but not with a diphosphine ligand. So if you look at the Cambridge crystal database, you find that's the gold-11 with a triphosphine. And what it turned out that, so this actual gold-11, it has a 2-chlorine ligand, right, as the inner shell. But just this gold-11 also has a 2-chlorine, but this 2-chlorine is actually labile. If you do electrospray, the new class that Jar discovered, the chlorine can come off. So basically, you can have just a bare gold-11 cluster with 4 ligands. But the previously known gold-11, the chlorine ligand are not labile. The structural change is very, very subtle. The arrangement of the gold-11 atom. So now, because now this chlorine atom is labile, that means in solution, that chlorine atom can come and go, right? It's just basically can dissociate. So then you can open up active sites. So Jia actually, he tried alkyne hydrogenation. He found that this is actually is a very good catalyst for semi-hydrogenation of polarized alkyne. Okay, not with acetylene, but you have to have a polar group on the triple bond. And he actually was able to show that you can form a very selective semi-hydrogenation. So he actually went on, he did all the calculations, the mechanisms. So this is also a very, very good cluster. So, but Jia has, he graduated, he moved on. And so, this project is more or less put on hold. So to just conclude this part, right, just for the students in this audience, right, there's still a challenge for you. There's still an opportunity. This is what we want to do, and we have not accomplished this. But along the way, because we use the new ligands, so my belief is that if you use a new ligand to make a gold cluster, you will make new clusters. So if we find the right ligand, this cluster, I think, is still achievable. But this will be for some of you to accomplish. All right, so now I want to come to the main topic of this talk. That's boron cluster. All right, so why boron? So this is the periodic table, a cartoon version of Professor Lipscomb's periodic table. All right. So you may see this is an odd periodic table, right? Because all the element is surrounding boron, because Professor Lipscomb won the Nobel Prize for boron chemistry in 1976. Of course, for him, boron is the center of the universe. I can say the same for me. For the past 2 decades, this is also true. So the question is why boron, right? So I already showed earlier that the carbon cluster gave us all this amazing nanostructure, right? So fullerenes, carbon nanotubes, new 2-dimensional materials. So the question we're asking is, okay, can other elements form fullerene-like structures or graphene-like structures? So we saw that the boron is the most promising element because of the strong boron-boron bond. So the question is, okay, how do we make boron cluster, right? So we have to use the same way. So we have to use laser vaporization because the boron has a very high melting temperature. It's very difficult to vaporize it, just simply heat it up, right? So we have to use a laser vaporization. And so this is kind of our beaker, right? This is how we synthesize boron cluster. So So we use the laser and we vaporize a small amount of the material, and we let the vapor to condense by mixing with room temperature carrier gas. Then basically now we are making a mixture of boron clusters, and then if we use mass spectrometry to detect what comes out, so this is a typical mass spec you will see for boron cluster. So this is from boron 8 to boron 42. So we don't really see huge variations like in the carbon cluster. So what we do is now we're going to do spectroscopy on this cluster, and one cluster at a time. Then we're going to combine computational chemistry to really figure out what are their structures and what are the chemical bonding. So this is the experimental schematic of the experimental apparatus. So we have the cluster source. This is a mass spectrometry, so we can separate the cluster, then we can select the one that we want to study, and then we illuminate it with another laser, and we knock electron out, then we measure the kinetic energy of the electron. That's how we do photoelectron spectroscopy. So basically, in photoelectron spectroscopy, what we do is we use a laser to knock electrons out of the valence orbitals. Okay, so in the very basic level, a photoelectron spectrum basically tells you about the quantized energy levels of the cluster of the molecule. Because these valence electrons, right, are responsible for the chemical bond. So essentially, we are directly probing the chemical bond, essentially. So photoelectron spectroscopy is the closest experimental technique that you actually can directly examine the chemical bond. So this is a calibration spectrum that we use. We usually use a copper atom or gold atom. So this also shows you how photoelectron spectroscopy works, right? So you look at the copper atoms, the valence electron configuration is 3d10 and 4s2. If you remove an electron from the s orbital, you see this beautiful peak that also tells you the electron affinity of copper atom. If you remove an electron from the 3d orbital, you have a 3d9 configuration, you get a W to D final neutral state, and you have a spin orbital coupling, and that's from the d orbital. So what we do is we measure the kinetic energy of the electron, then we obtain the binding energy of the electron in the anion or in the molecule. So that's we usually plot in terms of the electron binding energy inside the anion. So we also have a different version of photoelectron spectroscopy. We can do high resolution. This is using photoelectron imaging. So I will not say too much about this technique, but in this technique, we can transform photoelectron spectroscopy from electronic structure probe into vibrational spectroscopy, because in the imaging technique, we have wave number resolution. So that's close to infrared spectroscopy. So we can resolve all the vibrational features. But all the research I talk about today is actually done on the time-of-flight machine, so that has about 20 millieV electron energy resolution. So just to reiterate, so we use a combined experiment plus theoretical approach. So from the photoelectron spectroscopy, we measure the energy levels in terms of the electron binding energy. Sometimes we can get isomer information. Sometimes we can also get vibrational information. So from the theory, we want to get the energies, or the energetics and the structures, and we can compute the electron binding energy to compare with the experiment. And most important, then we can analyze the chemical bonding. We can analyze the electronic structure from theoretical calculations. So the very first boron cluster that we succeeded in making and studying is the B5 cluster. So this is the set of photoelectron spectrum we get. Okay, so at the different photon energy, so at the low photon energy, we actually have higher resolution. We actually can resolve vibrational feature even with the low resolution magnitude time-of-flight method. So from a calculation, we can get different structures, but what we are interested in, of course, is the most stable structure that we call the global minimum. The global minimum should be one that we make, and if the simulated spectrum of the global minimum agree with our experiment, then we know we have succeeded. We have find what's the most stable structure. So this is the global minimum. It has this planar structure, and these are the computed vertical detachment energy. So there's a very good agreement. So these are the valence molecular orbitals, and from this we can analyze the chemical bond. So of course, I have a set of amazing theoretical collaborations. So this effort in particular, we started to collaborate with Professor Alex Baldover at Utah State. And actually, his first graduate student to work on this is Anastasia Alexandrova. So she is now a professor at UCLA. But her PhD thesis basically involves the first few up to boron 9. So these are the boron classes that we have studied up to now, up to about 40 atoms. They are all planar, okay? So boron classes are planar. So this is Professor Alex Baldover. We have also collaborated with Professor Jun Li and Professor Xidian Li. So unfortunately, Professor Baldover passed away 2 years ago. But if you look at the bulk boron, right? The bulk boron has a very different crystal structure. It basically consists of these B12 icosahedrons. They are covalent linked. So this is a refractory material with a very high melting temperature, but in small cluster form, these are all planar, right? So if you even look at the B12, right? So that's B12. In the bulk, basically consists of B12 cage, but in isolated form, the B12 doesn't form the cage, it's planar. I want to select out a couple of these classes to talk about this. One of this is B36. B36, this is the photoelectron spectrum, and when we try to do global minimum search, we find the most stable structure actually is a planar structure with a hexagonal vacancy in the middle. And the simulated spectrum of this structure clearly agree with the experiment. We have other tubular-like structure and other planar structures, and their simulated spectrum clearly don't agree with the experiment. So we know that that's the structure of B36. And this was very exciting because now this is a planar actually. If we analyze the chemical bond, we find that the pi bonding of this B36 is actually very similar to this aromatic polyaromatic hydrocarbon molecule. So now this cluster, right, this is planar. So we can imagine, right, to use this as a building block, and you play checker game, you can actually make a two-dimensional boron. So why do we think this is exciting? So in fact, as long as B carbon nanotube was discovered, there were proposals to make boron nanotubes, right? So actually, one of this paper actually was by Professor Lipscomb. These were simpler, hand-built structures, right? They were using triangular lattice. What is a triangular lattice? Because boron is electron deficient, right? So if you form a hexagonal lattice with boron, you can form a 3-bond, but then the pz orbital is empty, so it's not stable, right? So in graphite or in carbon, you have a pz orbital, then that can form a pi bond with the nearby carbon. So, but on average in graphite, in graphene, so you have a 2 pi electron per hexagon. So to build a triangular lattice, right, you simply put a boron atom at each of these, the center of the hexagon, then you build a triangular lattice. So that's what these authors were using to build the boron nanotube. But boron has 3 valence electrons, so it's 2 electron rich. So this triangular lattice is 2 electron rich. If you actually optimize that triangular lattice, it's actually not a planar. It's rippled. So that's because it's 2 electron rich. So
let's go back. Yeah, what is the origin of this? The previous one. Previous image.
Which image? This one?
Yeah, that's right. Center, there's one atom missing, so-called missing.
Yeah.
What is the origin of
Yeah, just move. Just okay. So this is the origin, right? So if you have triangular lattice, it's 2 electron rich. It's actually not stable. So okay. So this is the triangular. It's not stable because 2 electron rich. So the next view graph. Okay. So in fact, in 2007, there were 2 groups. They reconsidered this. They said, okay, so the triangular lattice is not good to build boron nanotube because it's not planar. So you really want a planar structure to build the nanotube. So they realized that it's 2 electron rich. If you actually remove some boron atom from this triangular lattice to create hexagonal vacancy, you actually can find a perfect planar structure, and they actually are much more stable in terms of the cohesive energy. So this is one group. This is one group from Yale. This is a group from Tsinghua University in Beijing. These 2 papers they submitted about the same time, even though these appeared in 2008, but this is about the same time. So now our B36 cluster provide an indirect proof that this type of structure is what you want to build. This is why we saw that we can use B36 to build a 2-dimensional boron, but you need a hexagonal vacancy. So that's because if you don't have this vacancy, it's 2 electron rich, and it's not planar. So we saw that this should be able to be made. And so if we can make this material, we need to have a name. So we coined the name borophyne. And so we did B35, and B35 has an even simpler photoelectron spectrum. And in fact, if you just simply take B36, just remove another electron boron from another hexagon, you have 2 empty hexagons next to each other, and that's the most stable structure. You see, this is similar spectrum is in perfect agreement. So if we take this B35 cluster, right, with 2 hexagonal vacancies, you can build many different type of borophyne. In fact, computationally, many different kind of borophyne structures have been predicted. So when this paper was accepted, this is actually the end of 2023. It's right before the Chinese New Year. So we got quite a bit of press, and so you can't read Chinese here. So that's a borophyne. That's the Chinese translation of borophyne. So we actually made it to the front page. This is the Science and Technology Daily. This is a Chinese newspaper. Actually, I blocked this up, but what's behind here is the top Chinese leader, Xi Jinping, and they were celebrating Chinese New Year behind here. But this is our article, okay? Because the Jun Li's group, is from Tsinghua University. So when we coined this name, right, I Googled borophyne. Nothing came out, right? So 5 months later, right, this is May 23, so I Googled in Chinese, but there are 200,000 returns. So this, in fact, in China, just tell you how erratic the stock market. The stock market, the stocks for boron company, the company who marketed boron, and they were just going out of the roof because of they think of borophyne. So of course, Boron at the time also put up a press. So you can read here, okay, graphene, a sheet of a carbon atom, atoms may soon have a new nano partners. Actually, there was some comment from me. So basically, this is I cautioned that is if somebody can make it. All right. So the conclusion of this press release is okay. In light of this work, the prospect seems much more likely.
Did you make money?
I actually made negative money because I have to pay to publish that paper in Nature Communication. All right, so we did not have to wait long. And so in less than 2 years, 2 groups, they did exactly this. So this is a group from Northwestern and Argonne National Laboratory. This is another group from Institute of Physics in Beijing. And they simply they took a silver substrate, that's the most inert substrate, and they deposited the boron monolayer on the silver substrate, and they can make beautiful two-dimensional structures. And if you look at the high-resolution TEM, and you see these beautiful patterns, and if you simulate the image using this boron structure, you get a perfect agreement. So now boron has becoming a really active class of synthetic 2D material. Most of the 2D materials you hear, they come from the bulk 2D material. You can use Scotch tape to create them. But for boron, you have to grow them. You have to synthesize them. So this is a synthetic 2D material. I mean, I did have a view graph. There's a Florida company. They were marketing boron. They were selling this stuff. They said they have a boron from version 1 to version 4. This is a coating material for cars. If you have expensive cars, they claim if you coat it with boron, it can make the car shinier and the dirt wouldn't stick. Actually, I have that view graph at the end, but I saw that I don't have time to play that joke since you asked that question. Somebody has made money out of boron, but certainly not us. We didn't even patent that. Actually, the other company, they even trademarked boron. But I'm sure they don't have boron, but they have a borosilicate in that coating. So they do have boron, but no boron. All right. So boron, now is a new class of materials, but this is unlike a graphene, right? You can take a Scotch tape and you can make it in any lab. But boron, you need specialized high vacuum equipment to grow them. So, but nevertheless, there are actually quite a few groups now have joined this, and this if you look at the publications and the citations, it's a exponential growth. But ironically, right? So I did these Google searches last week. Our original B36 paper was not in this because the boron is not in the title of this article. So in fact, in our initial submission, we had the boron in the title, but the editor insists we don't put that title put the boron in the title. We only discussed this naming in the last paragraph, and consequently, if you actually look at the 2014 paper, is not our original boron paper. It's actually the Jack's paper on B35, because that paper we have boron in the title. But anyway. So let's move on, right? So the biggest cluster we have solved up to now was B48, and this cluster were predicted to have a bilayer structure. So we computed the anion also has a bilayer structure. So this is the photoelectron spectrum, and this bilayer structure seem to agree well with the experiment. So that means bilayer structures start to be possible for larger clusters. Now, if you extend this bilayer B48, actually you can make bilayer graphenes. This bilayer is not a van der Waals bilayer, right? So because you have interlayer boron-boron covalent bond. So interestingly, this same two group who initially discovered synthesized the boron, they reported that bilayer boron also exact the same time. It's interesting because in 2014, these two groups, the two papers submitted within 10 days. And this bilayer boron paper, they also are submitted within 1 week. So it's really interesting that I don't think they were communicating with each other, but they're clear there was some kind of a race, and they all submitted this paper at the same time. But anyway, so that's the story of boron. So I have 20 minutes, so I want to move on to larger boron class, right?
Time for questions also.
All right. So, all right, 10 more minutes.
Yeah.
All right. All right. So what about fullerenes, right? So we can make a boron, it's a graphene. Like, can we make boron fullerenes, right? So So this is the structure of a Buckminster fullerene. So you have 20 hexagons, 12 pentagons. But we know B60 can't form this structure the same way that boron cannot form a hexagonal lattice. Now, if you put one boron atom at each hexagon, so you ended up with B80, and B80 will have exactly the same number of valence electron as C60, 240. So the question is this possible? And in 2007, this group, the group Jacobsen is from Rice, they published a paper. They suggest that this actually is stable, but it doesn't have icosahedron symmetry, it has a tetrahedral symmetry. But actually, Professor James's group immediately published a paper. For even larger boron cluster, they indicated that actually this core shell structure is more stable. So this is B84. You have B12 icosahedral core then with another shell. So this is all hand-built structure, but this is also hand-built structure, right? This is not a global minimum search, but of course B80 you would have 2 to the 80th possibilities, right? So global minimum search is quite challenging. Actually, subsequently, there are many groups who attempt to do global minimum search for B80. So this is one of this paper from Goey-Decker's group, and they find that through global minimum search that there are many, many other structures which are more stable than the buckyball structure. That's the bucket. If they use buckyball as a reference, there are probably hundreds of other structures which are more stable. So the most stable one is actually core shell structure. So this is a low symmetry. So Professor James built is a high symmetry structure with the appropriate numbers, but this doesn't have the right number. It has a very low symmetry. So actually, the first boron fullerene or the first boron cage we made actually were B40. So this is the photoelectron spectrum of B40. So we actually find a very weak peak at a very low binding energy, right? So boron clusters, they tend to have very high binding energy. But at B40, we have a cluster with a very, very low binding energy. And we know this is an isomer. This is a no, so there are 2 isomers. So the majority of this is this species, and there's a minority isomer has this structure. So when we try to do global minimum search, we find in the anion, actually, the planar is the most stable, and then there's a cage structure with the low-lying isomer. But in the neutral, though, the cage is the overwhelmingly the most stable structure. So it turned out that the cage structure has very large homonormal gaps. This is about 2.5 eV. So that means the cage is extremely stable electronically. So in the anion, you put the electron in the LUMO, which is unstable, so that makes the anion for the cage less stable. So this is the planar structure with a double hexagonal hole, so that agrees with the majority of the spectrum. So, but nevertheless, so this is the first boron cage we find, so it has a D2D symmetry. There is no localized boron-boron bond, right? So you have delocalized 3 center bond, and then you have a completely delocalized pi type of bond, because this is a sphere, so you can have a pi type of bond. So if you compare it with the C60, so this is B40, it's slightly smaller, it's 0.6 nanometer, so carbon 6 is 0.7 nanometer. So the question is it possible to make this, right? So there are different suggestions. Okay, you can try to stabilize it, maybe by doping. Actually, Professor James has the best suggestion. He thinks that, okay, if you can put this organometallic kind of compound actually to cap some of these hexagonal vacancies, you might be able to stabilize this. All right, so what about larger boron clusters? All right, so okay, let me just skip this. So the question still in our mind, even back in 2004, was, okay, so when will the 3D structure appear, right? When will the bulk like B12 dodahedral structure appear, right? The B80, the global minimum suggested already had this B12 unit, but that's, what is the smallest, what's the size that this appears? So this question, so we know that as a function of size, eventually this cluster they should become 3D, and eventually this structure should appear. That's why, in 2014, when we found B36 were still planar, we were actually quite astonished. That you could have 3 B12 unit, but nevertheless, it's planar. So when we moved on, so we found the B41, B42 are still planar. But there's a problem. The photoelectron spectrum for the large boron cluster become extremely complicated. So actually, back in 2011, we did a quick search of the large boron cluster. We found this type of structure. So this is essentially, it's useless, right? There's no information in this type of spectrum. They're just a blob. So the problem is that we can't create a cold cluster. This is a very large cluster. If you just think about the heat of formation in this system, right? You add 1 boron atom, you add about 5 eV of energy. So if you have 40, 60 atoms, when they are forming, there's enormous amount of heat of formation you have to release. So we tried the different ways to cool it, and we finally realized if we have argon in the helium carrier gas, that we can create a colder cluster. So I have an amazing student, Hyun, he just graduated, and this is a new student, Dennis, joined him. So we find if we use argon in the carrier gas, we can actually get spectrum which is better result. So that means we have colder cluster. This still doesn't mean this is very cold, but at least it means this is colder than those probably are very hot. This is colder.
Would krypton be better still?
It could be, but it's expensive, and Xena might be even better. So let's stay with the argon. This is still affordable. Even neon is not affordable anymore because neon is imported from Ukraine and the price was just going out of the roof. And these spectrum are still complicated, okay? And we have features, they don't all look the same, but so what this means, we need other experimental technique. Okay, so my time is running out. Let me just say that we were able to collaborate with the group in China. They were doing chem-absorption experiment. They find that in reaction with ethylene, this B46 is reactive, B56 is reactive. And they were able to do kinetics. They found there are different isomers. So this gave us a hint, right? 46 is probably where the 3-dimensional structure appears, because we know the small clusters are all planar. They are not reactive. So that means the planar borons are not reactive. So the reactive one must be 3-dimensional, that they probably have low symmetry. So there are active sites on the surface that's reactive. Actually, B56 is even more striking in the CO2 reaction. Among all up to B68, only B56 is reactive with CO2. So it must have a very special structure. So we did a global research and find, indeed that all the low-lying isomers are 3D. So this is B46. It's a very low symmetry. That's C2 symmetry. There are 2 boron atoms in the middle with the 44 shell. There are really very low symmetry and protruding boron atoms on the surface. They should be the reactive side. And the B56, the most stable structure, is the one actually which has a B12 unit. It's like a bird's nest. You have B12, then with a half shell. Now, the photoelectron spectrum alone, we could not have reached the conclusion because this is the photoelectron spectrum. It's very complicated. We know we have different isomers, but to be certain which isomer is very critical. But we know that the global minima, this structure is in the spectrum, and this is in the spectrum. So, but now with the chem-absorption experiment, that we know that this structure, they have to be correct. All right, so we of course, then this structure, right? So they have to be able to explain the chemabsorption properties. We did the calculations on the chemabsorption properties, so everything is consistent. We did the bonding analysis. So this is B46. The B56 is more interesting because indeed you find this B12 unit. So you have all this delocalized bond of the B12 unit, then you have the bond on the half shell. So basically, to conclude that we now have found the 2D, 3D transition. It's at 46, and B56 is likely the smallest cluster that you have the bulk-like structural feature appears. But this transition is not smooth. It's not like, okay, B46 is 3D, then everything is 6D, right? I already showed that B48 actually is bilayer. But from 46 to 56, in this range, only 55 is slightly reactive, right? All the other clusters are not reactive. So that means that they could still be planar or they still could be bilayer. So what this means is for larger clusters, right, there could still be more exciting structures, nanostructures. They may not be all just these boring bulk-like features. So anyway, so let me just stop here, and I'm not going to repeat all these conclusions. So let me just thank the funding agency. This project has been supported by ASF as of now. And these are all my theoretical collaborators and the people who, of course, this is through generation of students, but currently is Hyung, and he just graduated, so he's going to do a postdoc with Mark Johnson soon. And this, Dennis is taking over this. So Han Wen actually worked on a different, on the high resolution project, but he participated in this experiment. So he's already started his postdoc at Columbia. Anyway, with that, I'm going to stop. So I have 8 minutes for questions. Thank you.
So I want to ask about this Boron.
Mm-hmm.
So if we compare the Boron with suppose graphene, so graphene has many applications as a semiconducting material, but we are doping the graphene for using meaning of N-type or a P-type material. But so if we think about the Boron, there is a vacant P orbital maybe. So we should not need a doping for that. Like we can directly use this material as a semiconductor.
That's an interesting question, right? So boron, it turned out that the most common one, the one that have been synthesized, they actually are metallic. So there have been theoretical predictions, right? So because you can have a different arrangement of the hexagonal vacancy, or you can have a different density. There are certain configurations that could be semiconducting. But the problem with this boron is, when you synthesize it, right? So the challenge is how do you control what structure you make? So currently, I think that's still a challenge. I think the challenge is the same as a carbon nanotube. In fact, when you make a carbon nanotube, you actually make a mixture of many different diameters, different helicity. So boron, I think it's the same challenge. Graphene, there's only one structure. There's no ambiguity. But for boron, you can change the conditions or change the substrate. You may be able to make different structures. But I agree with you. The exciting one is the semiconducting one. But all the synthesized, observed boron, they are metallic. They are all metallic. They are better metals than graphene, though. So they are much better conductors.
Thank you, sir, for a very interesting talk. I was wondering when you discuss about the whole 22 clusters, where the fusion is happening between two core along the square plane. So can we generalize this rule for the James-Mingo formalism to give some kind of rule which follow the nanocluster also, like boron cluster follow?
If I understand your question, you meant that, okay, so we have this gold 11 fused together, and at the interface, we have uncoated in the gold. Can we generalize this?
Where you have shown like 4 hydrogen bonded.
Yes.
And during the crystallization is not.
Yeah.
So that how the formalism is happening?
fusion rules.
There are fusion rules. Well, if there is any rules, it seems like this gold 11 is very stable, and we have many different attempts, and we seem to always make this gold 11 dimer, right? So the initial one was gold 22 share a square face, and the second one we made actually is still gold 11 dimer, but sharing a triangular face. So is that a rule? I wouldn't say that's a rule. So can we generalize that? I guess you say to make trimers or tetramers, right? That we don't know. We did not observe it. So this is not entirely by design. So I still think that there's a large part, at least for the boron ligand, right? So I think the SIO ligand has been investigated much more extensively, but the phosphine ligand, even though they were the earliest ligand to make a gold cluster, no nanocluster, but gold clusters, even in the late 60s and early 70s. But in the atom precise community, right? So phosphine is not the ligand of choice, I think. But I think there is still a lot of room so to play. It's going to be a ligand selection rather than you can view that as a design, but it's usually is a post design, right? So I don't think we have some ideas. Can I design a synthetic process to make my gold 20? If I knew how to design that, we would have made that 20 years ago, right? But I still think it's going to be try and error, and it's a discovery process. So it's going to be very, very difficult to design. If somebody tells you that, okay, they made that beautiful structure, that's exactly what they designed, most of the time they probably are lying because they are rationalizing what they have made, right?
On the same lines, like when you are saying the hydrogen is going during the crystallization,
Yeah.
I doubt like maybe the hydrogen is there and you are not able to refine because it is very close to the gold. Gold has very high electron density, so hydrogen will be buried inside that. For that you have to go to neutron or maybe neutron denser.
No, the hydrogen is gone. There's no question it's gone. It's gone. We can't detect it. It's not in the mass spec. It's not in the AMR, right? So we know that the hydrogen is gone. It's metastable. Because as I mentioned, even while we are taking the AMR spectrum, right, during that time scale, hydrogen is coming off. So the hydrogen is metastable, there's no question. For the tetrahydride, it's metastable. For the trihydride, it's stable. It's very stable. The tetrahydride is metastable. So the hydrogen did not go inside. There's no inside for the gold cluster. The hydrogen is gone. Yes.
There are several clusters wherein it can be there. There are several others which is quite labile. There are clusters wherein hydrogen has been solved, but that is not always true of any cluster.
There are not that many gold clusters hydride, all right? So Kuda made the gold 9 in 2019. So that hydrogen is even more labile. So it's much less stable than the gold.
DN has
22.
a compilation of those for which structures are used.
Mostly it's copper hydride is more common. Silver hydride is less common, but more common than gold. But the gold hydride, I would say our gold 22 tetrahydride was the very first one hydride, right? So bulk gold, you can even do the things at a high temperature and high pressure. Gold would not form a hydride. It just doesn't form a hydride. So hydrogen does not dissociate on gold even at a high temperature. So yeah.
You mentioned about this gasless 2D to 3D transition for boron is around B46, right?
Yeah.
But while the solution phase is pretty early, like is it just a chemically active, like the environment is?
Yeah. So in solution is a complete environment. You talk about the borons, right? So borons then it terminates the dangling bonds, right? So in isolate is the case, right? So the atoms are trying to juggling their position, trying to find the most stable configuration. So I think the 2D, the planar structure is the best way. So essentially, it's electron sharing, electron delocalization. It boils down to electron sharing, electron delocalization. And in 3D, to form this cage structure is the best way to share electrons. So in those cages, all electrons are shared. So I think in finite system, the two-dimensional structure is the best way. Now, if you add hydrogen to terminate those dangling bonds, then they basically behave like a bulk, right? So in fact, the B12H12 boron was the first predicted computationally, right? Using MO theory, they simply take out this B12 unit from the bulk, then they terminate the surface with hydrogen, right? This was first predicted by Christopher Locke-Higgins before it was synthesized. So it's a completely different environment, right? So Professor Sauder-Gauche, right, is trying to make new boron compound, right? So all his compounds are terminated with hydrogen, and they. So basically, another way to look at it, if you give boron an electron, it behaves like carbon, right? So BH unit is also isoelectronic to carbon. So then its behavior will be completely different from this isolated cluster.
Well, I think it was a great feast.
Thank you.
Fantastic. Your attachment to photoelectron spectroscopy is very, very, very. I know this for many years. Your attachment to transition metals is also very much known to me. You then went to carbon. Why did you choose boron?
So I thought I made it very clear why boron. Yeah. Yeah. So we think that boron is the most promising element to. So this is the question, right? So the motivation starts from carbon, right? Can other element forms structures like carbon? This is the fundamental question. So this is right. Boron, it has a strong bond, and it can form polymer. Nitrogen bond is the strongest bond, right? But nitrogen terminated at N2. But the boron doesn't terminate. It have strong boron bond. It doesn't terminate at B2. It forms solids. And so that is what we think that is most promising. Now, if you think about the melting point, of course, tungsten has or tantalum, they have the highest melting point, but these are transition metals, so they are different. So we think boron, among the main group element, is the most promising one. Of course, BN is equivalent to C2, so boron nitride is the same as boron, right? But that doesn't really count. So the boron, on the other hand, if you give boron one electron, like I mentioned, right? So it's like a carbon. So in magnesium diboride, you have this hexagonal boron lattice, right? Exactly like graphene. So if you give boron an electron, then it's not special anymore. It's just like carbon. So this is a region of what we're really interested in. So can we find similar structures as the carbon, tubes, cages, and so it's because of the strong boron bond. So we think that.
Questions give great insights to students, and that is the reason why I'm asking these. Lai-Sheng, you could have easily gone to silicon, right? Natural.
We did the silicon, but they were boring.
Thank you.
That's an excellent question, Pradeep. So because we tried the silicon become tetrahedral even at tetramer, right? There's nothing really special. So